Okay, so this is the homework solution for the next week, for test number two, I should say, on, which covers projectile motion and basically Newton's laws and the application of the second law without friction. So the first problem was you had this projectile that was launched from the edge of the roof of a building, and you knew basically how far, basically where it landed on the ground. So it lands over here, 115 meters horizontally from the base of the building. And you also know the angle that it landed here. And the first question is, what initial speed was it launched at? Okay, so we're trying to find the magnitude of the initial velocity here. Okay, so the basic idea for this is we want to find the magnitude of the velocity. You need to know basically its x and y components, right? If you can find how much it is in the x direction and the y direction initially, then you can use that to find the magnitude of the initial velocity. So the idea is whenever you're given a horizontal displacement, you should always look at that right away and see if you can find any information that you didn't already know. Hold on, this is my antivirus thing. Okay, great. Okay, so all right, so the idea is that it starts horizontally speaking. It starts here, right, horizontally, and then it ends up over here. So the delta x is 150 meters for it. And there's only one equation for delta x. It's delta x is v0 x over t. So if you divide delta x by t, where t is the time in the air, it was in the air for, which was given to you, it was 5 seconds, you can find the initial velocity in the x direction. So you know the initial velocity in the x direction, what the x component of this v0 is, but you also have to find v0y to finish it. Okay, but then you say, okay, what other information do I know? Well, I know the angle it hits the ground at. Can I figure anything out, with that angle? Well, you can if you sketch. It's a pretty bad sketch, but if you sketch the final velocity vector, which is this vector here, it's at 60 degrees below the horizontal like this, right? It's just this vector here. But we know that the final, x component of the final velocity vector is going to be equal to the initial x component, because the velocity vector in the x direction doesn't change. So if it was originally 23 meters per second over here, it's also 23 meters per second over here. So we know that this is 23 meters per second. We also know this angle. So therefore, you can figure, just using trigonometry tangent, you can find what VFY is. Right, so that's something else you didn't know. So the tangent of 60 is VFY over VFX. I put a negative when I saw for VFY because it's going down. And that gives you what VFY is, what the y component of the velocity is when it hits the ground. Now the question is, can you find the initial y component? Well, you can, because VFY is equal to V0y minus GT for projectile motion. So then you just solve for V0y, it's VFY plus GT. And you plug in the numbers and you get what VOY is. So that gives you the magnitude of V0, because it's the x part squared plus the y part squared square root. So that's it. That's how you do it. So what's the key things here? One, if you're given an angle, you might want to look at that to relate the x and y components of the velocity to one another at that angle. Two, a big thing is if you're always given delta x, or if you're given a delta x or asked to find a delta x, you should always immediately look at this equation here to get, to see if it can either answer the problem that you're asked or give you some additional information that could be used to, answer the problem like it is here. And, you should know how to use this equation, and you know how to find the magnitude of a vector, which isn't hard because it was on test one. So part B is pretty easy. What's the angle? Once again, this is a pretty bad sketch here, but you get the idea. So V0x and V0y. We just found it. So if you want to find the angle of v0, it's the inverse tangent of v0y over v0x. Pretty straightforward. C was what is the height of the building? Okay, so the idea is that what you're trying to do is find the delta y until it hits the ground, because that gives you the height of the building, right? Because it goes from the top of the building to the bottom of the building. So it goes down the height of the building. So you know the time it's in the air for, you know v0y. So if you know those two things, you can find delta y. You could also use vfy squared is equal to v0y squared minus 2g delta y. That's another thing you can use. But the other, we know the time it's in the air for, and we know v0y. So that's the equation we're going to use, which is this. So you get negative, which means it goes down 76.56 meters, but obviously the height is 76.56 meters. And the last question was, what is the maximum height above the ground the projectile goes? This here, if I go up here, what's this height from here to here? Okay, so it's the same basic idea as free fall. At the top here, the velocity in the y direction, not the velocity, because it's still going in the x direction at this point here, but the velocity in the y direction is 0. So you set this equal to 0, solve for delta y, it's v0y squared over 2g. This gives you the maximum displacement, which is the height above the roof here from here to here. So if you want to find the height above the ground, it's the height of the building, which we found in the last part, plus this delta y, which is 80.89 meters. So you should know how to do the examples we did in class, and also this kind of example. There's another example in the next homework assignment, but I'll post some extra examples too from another class, so you see a few more examples of projectile motion. But you should know how to do the one we did in class and this, and know what's going on for these projectile motion problems. Okay, so let's go on to, and this one's a little bit more. Okay, so the idea is you're dropping, or not dropping, you're throwing a ball down, and from the top of a building, I should say, it's 150 meters high, and you're over here and you're firing a projectile at some velocity and some angle, and you want this projectile to hit this ball when it's 10 meters above the ground, and this projectile is 125 meters away horizontally from this ball at the base of the building. All right, so the question is, how on earth do we do this? Okay, so the first thing we want to do is figure out how long it takes the ball to fall to this point here, 10 meters above the ground. Because this projectile has to hit this ball in the same time. In other words, if this takes 5 seconds to fall, this projectile has to go from here to here in 5 seconds, right? That's the point. So this is just a free fall problem. The delta y, since it has to go 10 meters above the ground, it goes 140 meters down, because it's 150 meters minus 10 gives you 140 meters minus 140 because you're going down. It's just a free fall problem too. It's what was on test 1. So this is ball 1. I call this object 1. So you have vf1 squared is equal to v01 squared minus 2g delta y. This is just a free fall equation. And then I solve this equation for vf1, which is the final velocity. It's negative because it's going down. Oh, I didn't mention why I'm doing this. I'm doing this because I can use this to find the time. That's why I'm doing this. As it's written here, but I didn't mention it. So then I plug in the numbers. Remember, delta y is negative. This v0 is also negative because you're throwing it down, but it doesn't really matter for this. And you get negative 53.35 meters per second. So this thing is moving at 53.35 meters per second down at this point, 10 meters above the ground. And then you plug that into the free fall equation for velocity. The final velocity is equal to the initial velocity minus gt. So you solve for t. Plug in the numbers. You got to remember v01 is negative, right? It's a big thing. If this was positive, if you write it as positive, you get a completely different time. So it's 4.42 seconds. Okay. That means that it takes 4.42 seconds for the ball to get from here to here. And at that same time, the projectile has to go from here to here, which means it has to cover this horizontal displacement. Once again, we're given the horizontal displacement in 125. Sorry, has to cover 125 meters horizontally in 4 point whatever it was seconds, 4.42 seconds. So you can use this to solve for v0x, right? Just like we did in the last problem. So it's the horizontal displacement divided by the time it takes to get there, which in this case it has to be 4.42 seconds so that it hits the ball. So the x part of the velocity has to be 28.28 meters per second to cover that displacement. But not only that, it has to be horizontally that far away, but it also has to be vertically 10 meters above the 10 meters above where it starts, right? It starts here. If it's to collide with this ball 10 meters above the ground, then it has to be vertically, or the delta y has to be plus 10 meters for the projectile. If it's in the air for 4.42 seconds, the vertical displacement has to be 10 meters, is what I'm trying to say. So we can use the delta y is equal to v0yt minus 1 half gt squared to find v0y. That's what v0y has to be, such that the delta y is 10 meters if it's in the air for 4.42 seconds, right? So basically, you just solve this equation for v0y by doing a couple steps of algebra. You plug in the time that we just found, and delta y is plus 10, and that gives you v0y. So once you know v0y and v0x, just like the last problem, you square them, add them together, take the square root, and that gives you the speed that it's launched. Part B was what is the angle that it's launched. So it's just the inverse tangent of v0y over v0x, just like we did in the last problem. So to put these 2 points together, if you launch it at 37.06 meters per second at 40.25 degrees, it'll be in the air for 4.42 seconds. In that 4.42 seconds, it'll travel a horizontal displacement of whatever it was, 125 meters, I think, or 115, I don't remember actually. 125 meters. And 4.42 seconds after it's launched, it'll be at a vertical displacement of 10 meters. So both balls will collide at that point, right? That's how you do that one. It's a little bit weird, but that's how you do it. So part C was what is the velocity at the ball. So the x component of the velocity doesn't change, right? So whatever we found from part A, it's the same thing. For part B, for the velocity in the y direction, I should say, it changes, right, because of gravity. So it's the initial velocity, which we found in the last part, minus, or the part before the last part, minus g times the time it's in the air for, the time until it hits the ball. So it's negative 19.42 meters per second. And then if you know the x component and the y component, you can square them, add them together, take the square root. That gives you half the speed that it hits the other ball at. So it's hitting the other ball at 34.31 meters per second. And the angle it hits the ball at is, once again, the x part of v0, vf, and the y part of vf. So you do the inverse tangent, and you get 34.40. It's just coincidence that the v and theta have almost the same number. But you have 34.47 degrees below the horizontal because it's past its, maximum displacement, and it's coming back down. So it makes sense that the velocity is below the horizontal. So that's how you do that one. It's another problem where, it involves a lot of sort of techniques that we use for free fall and projectile motion, I should say. But once again, if you're given a delta x, you want to look at that to see if you can find some other information. If you're given a time, you should see, okay, what can I find with the time? Just take some practice, but hopefully this makes sense when you see it. And, you know, you can do something not quite as complicated, but something like it on a quiz or a test. Okay, so let's go to number 6. All right, number 6 was combination projectile motion and Newton's second law. So if you have a mass on an incline without friction, the acceleration, I think we saw this problem in class, is just due to the x component of the weight, because you use this coordinate system here, and you have normal force going up and the weight force going down, and you have a wy and wx part of the weight. And the wx part of the weight is the only thing going down the incline. So this is the only force which contributes to the acceleration down the incline. So wx is, you know, w sine theta, as we saw a bunch of times. And that's equal to ma, because the acceleration is completely in the x direction, or down the incline. So you get a is g sine theta. In the y direction, there's nothing interesting happening, but you can find the normal force. Oh yeah, that's right, I forgot this problem. You're given the normal force, and you want to find what the acceleration is. I forgot about that. Okay, yeah. So the normal force is in the y direction, positive y. The y component of the weight is negative y. So you get Fn minus mg cosine theta is equal to 0, because it's not coming off the incline. So Fn is mg cosine theta, and if the normal force is half the weight, then you set this equal to half the weight, which is mg over 2. The mass and g cancels out on both sides, and you just get the inverse cosine of a half, so it's 60 degrees. So basically, if this angle is 60 degrees, the normal force is half the weight. Now, if the angle is 60 degrees, then you plug it in here for the acceleration, and you get the acceleration is 8.50 meters per second squared. Now, what we want to do is find the velocity at the top of the incline. So the velocity at the bottom of the incline is given. The length of the incline is given, and you're trying to find Vf. We also know A is going down the incline. So using these equations, this is a constant acceleration problem where x, remember x is, you know, parallel to incline. But essentially it's a 1D equation. You're just going up the incline in 1D. You go up or down the incline. So you can use v squared is equal to v0 squared plus 2a delta x. Delta x is the length of the incline. However, I got to go over that for 1 second. Anything going up the incline is negative. So v0 is technically negative, but you're squaring it, so it doesn't really matter. But you're going up the incline, right? So whenever you're going up the incline, your delta x is negative, because you're going up, not down the incline. So delta x is minus L, where L is the length of the incline. So you get v is negative v squared, v0 squared minus 2LA. And it's negative because you're going up the incline. That's where that negative comes from. You're going up the incline. Then the question is, how high does it go relative to the base of the incline? Well, it goes, now it becomes a projectile, right? And it's moving at this speed at the same angle as the angle of the incline. So the question is, how high does it go? Well, you can find delta y for the projectile. It's v0y squared over 2g, because at the maximum height or maximum displacement, vfy is 0. And the v0y is v0 sine theta, where theta is the angle in the incline, and v0 is this. It's the velocity that it leaves the incline at. So that gives you delta y, but then you add the height of the incline, which, if you know the length of the incline and this angle by trigonometry, is L sine theta. So it's 38.73 meters is how high it goes. So then the next question was, if you're applying a force up the incline and you want the acceleration to be g over 2 up the incline, what does that force need to be? So it's pretty straightforward, right? We know what wx is. It's mg sine theta going down the incline, so positive x. So if the force is applied up the incline, this is a negative force in the x direction because it's going up the incline. So in the x direction, you have mg sine theta minus f, because this is going up the incline. has to equal minus ma, because you want it to accelerate up the incline at g over 2. So that's a negative acceleration. Okay, so then you just find f. You add mg sine theta to both sides. Sorry, you're trying to find f. So you add f to both sides, and you add ma to both sides. And you get this equation here. Then you plug in a as g over 2, because that's what you want it to be, half of g. And then you, I factored out the mg, because there's mg here, there's mg here. So you get sine of 1/2, sine theta plus 1/2. And the angle is 60 degrees from part A. So you just plug in the numbers, and you get the force. So it has to be 268.01 newtons to move this thing up the incline at, to accelerate, I should say, up the incline at half of g. So once again, you should know how to do Newton's laws, sum of the forces, set it equal to ma. Know that a is constant, and then you can use that constant acceleration with other equations to find the velocity at the top of the incline, at the bottom of the incline, the time it takes to go up the incline, the time it takes to go down the incline, all that kind of stuff you can do. All right, the last, oh no, there's another part of this one. Yeah. So this is a static equilibrium problem. So you have these two ropes. And you want to find the mass of the sine. So it's very similar to what we did in class, except you're trying to find one of the angles isn't given, theta 2 isn't given, and also the mass of the sine is not given. But it's the same basic setup as what we did in class. So you have the tension, the two tensions, T1 going like this, T2 going like this. This is rope 1, this is rope 2. So the x part of T2 is in the negative x direction, and the y part's positive. T1 has a positive x part, positive y part. The x parts are both cosine. The y parts are both sine because they're opposite. So that's where T2x is minus T2 cosine theta 2 comes from. And T2y is plus T2 sine theta 2. T1x is plus T1 cosine theta 1. And T1y is plus T1 sine theta 1, which isn't anything new. It's just exactly like what was done in the notes. This is a typical coordinate system, obviously. And the weight of the sine is going down. So you want to add up the x parts and the y parts. So the x parts is just T1x minus T2x is equal to 0 because the sine isn't moving, it's in equilibrium, which means the acceleration in the x and the y direction is 0. So this is what you have here. So you know T1 and T2 for this case here. So you want to find that, you can use that to find theta 2, what theta 2 needs to be. So theta 2 is just the inverse cosine of T1 cosine theta 1 divided by T2, which gives you 46.83 degrees. So this angle here is 46.83. And now that you know the angle, if you sum the forces in the y direction, which is T1y plus T2y minus w, and that's equal to 0 because the acceleration in the y direction is 0, as it almost always is. The only thing you don't know in that equation is the mass. So you get this equation here, T1 sine theta 1 plus T2 sine theta 2 minus mg is equal to 0. So you add mg to both sides and divide by g. You know everything here except for a mass. You just solve for the mass. It's 26.59 kilograms. Part B is if you pull down on the sine with an extra force. What's this tension now? So if you pull down on the sine, both the tensions change. It's not going to be the same tension in as you found before. T1 and T2 are going to be different because you have another force pulling it down. All right, so the idea is it's the same thing as part A, except you have an extra force in the y direction, in the negative y direction. So the only thing that changes is that there's an extra force in the negative y direction. That's it. Everything else is the same. So in the x direction, it's the same thing as part A. You get T1 cosine theta 1 is equal to T2 cosine theta 2. Then in the y direction, it's the same thing, except you get an extra force of minus F. here. Now the question was, what is T1? Okay, so I don't know T1 or T2. So what you can do is you can solve the first equation for T2 and then plug that in for T1. And then what that does is it gets rid of everything but T1. You know both the angles, you know the mass, and you know the force. So when you do that, that gets rid of every expression but T1. So it's T1. So instead of writing T2, I write T1 cosine theta 1 over cosine theta 2 here. And then I have a sine theta 2 left over. So this becomes tangent of theta 2. Then I factored out the T1. So you get T1 sine theta 1 plus cosine theta 1 tangent theta 2 is equal to mg plus f. And then you just divide by the parentheses, and that gives you what T1 is now with this extra force. If you wanted to find what T2 was, that was another question. You plug T1 in here, you multiply by the cosine of theta 1 and divide by the cosine of theta 2. But, it sounds complicated, but all it is just finding the x and y components of all the forces, adding them up. You got to be really careful for with the signs, because if a component's in the positive x direction and if it's in the negative x direction, you have to write the signs down correctly. Or likewise, if it's positive y or negative y, you have to write the signs down correctly. But once you do that, all you do is just write down, sum the force in the x direction, set it equal to max. Sometimes ax is 0, sometimes it's not, but you just write it down. You sum the forces in the y direction. Almost all the time, those are equal to 0. And then you just do algebra to figure out how to solve for what you don't know. And that's how you do all these Newton's second law problems. It's the same recipe basically for all of them. Every single one is the same thing. The most important thing is to get the components right. Once you have the components right, it's actually not so hard to do these problems. So number 7 looks like it's a pain, but it's actually not. Once again, we're just going to sketch the forces on all the masses and apply Newton's second law to all 3 masses and see what we get. That's it. So let's sketch all the forces. Okay. Okay, so we know that we know the direction for acceleration. We didn't have to guess it. This one's going up at g over 2. These are going down at g over 2. Okay, so that's where the acceleration vectors come from, which comes up later. Okay, so these two things are on an incline. So we're going to use our own coordinate system for mass 2. X is down the incline, remember. X is always down the incline. So if mass 2 goes down the incline, it's positive x. If it goes up the incline, it's negative x. And then the same thing for mass 1 and mass 3 on this side. Positive x is down the incline. So if mass 1 or mass 3 go down the incline, it's negative. It's positive, sorry. If it goes up the incline, it's negative. Okay, so then we draw all the forces. You have a normal force on mass 2, the weight force on it. You have the x and y parts of the weight force, which are the same thing as what we've done, for every single problem on inclines. The x part is positive and it's sine theta, and the y part's negative and it's cosine theta times w. Sorry. You have 2 ropes. This is rope 1. So there's a tension on mass 2 going away from the mass along the rope, which I call T1. This tension is negative, though, because it's going up the incline. So these are all the forces acting on mass 2. Mass 1 is connected, the other end of the rope is connected to mass 1. So the mass 1 has a tension on it going up the rope, along the rope. And the amount of the tension is the same as this tension here. This is also a negative, going in the negative x direction because you're going up the incline. And then you have a normal force and a weight force for mass 1. Just like mass 2, right? Once again, the x part is given by W1 sine theta 1, and this one is W1 cosine theta 1. Negative W1 cosine theta 1. And theta 1 is this angle here, theta 2 is this angle here. I forgot to mention that. Because this mass is on this side here. It's going to have theta 2, and this mass is on this side here. So this is theta 1, and this is theta 1. But there's another rope here that's connecting these two masses. So there's another tension. This is a second rope, so I'm calling this T2. So there's another tension acting on mass 1 called T2, pulling it along the direction of T2, or rope 2, I should say, away from it. So this is a positive tension in the x direction because it's going down the incline. Lastly, mass 3 has a normal force, a weight force, same as W1 and W2, same form as them with different weight because it's weight 3, but the same form, and has a tension because it has a rope here connected to it. So the tension goes along the rope away from the mass. This is another negative tension in the x direction because it goes up the incline. Anything up, this tension here, this tension here, this tension here is negative in the x direction. So let's sum the forces in the x direction. So we're asked something about the acceleration or the tension. And the tension and the acceleration is all in the x direction. So we don't need to worry about the y direction for this problem. Just the x. So we're summing the forces in the x direction on mass 2 and mass 1 and mass 3. So we're doing mass 1 first in order. So you have T2 minus T1. T2 is going down the incline. T1 is going up the incline. Minus W1x, or minus M1g sine. Sorry, plus M1g sine theta, because W is going down the incline, is equal to MA, and A is positive because mass 1 is accelerating down the incline. So that's where this equation comes from, which I call equation 1. In the y direction, nothing really is going on, except you can find the normal force on mass 1. But we're focusing on the x direction. Then we're doing mass 2. So mass 2, the force acting on it is tension 2 going up in the x direction, I should say. So that's negative, and W3x is, of course, positive. Those are the only two things in the x direction. So you get W3 sine theta 1 minus T2, which is down here, sorry, this is mass 3, is equal to plus M3 times A, because its acceleration is going down the incline. That's positive. For mass 2, the only thing acting on it in the x direction is T1 and W2x. So W2x is positive, so it's positive W2 sine theta 2. And T1 is negative because it's going up the incline. So you get W2 sine theta 2 minus T1 is equal to MA, but A is negative, or M2 times A, I should say, because it's M2 times the acceleration. But A is negative because it's going up the incline, which is where this one comes from. And then what you're doing is you're putting those three equations together, which is what I have here, and you're trying to solve for the thing that you're trying to solve for, eliminating everything you don't know. So what I did is I plugged 3 into 1. So what I mean by that is T2 is N3g sine theta 1 minus N3a from equation 3. I solved this equation for T2. I added T2 to both sides, and I subtracted M3a from both sides. And then what I'm going to do is I'm going to put it in here. So this is what I did here. I have M1g sine theta 1 plus M3g sine theta 1 minus M3a minus T1 is equal to plus M1a. And then I still have equation 2, which I'm going to write beneath it, which is M2g sine theta plus T1 is equal to minus M2a, which is this. Then I multiplied this by negative 1, so this becomes minus M2g sine theta 2 plus T1 plus M2a. I did that because I want to cancel T1. You get this. And then I put, the goal is to find mass 3. So I'm putting everything with m3 on one side. Uh, so when you multiply this through, you get m3 g sine theta 1 minus m3a. So that gets pulled out on this side. Then I'm adding m2g sine theta 2 to both sides, and I get this. And where did this come from? When I multiply m1 times g sine theta 1, I get m1 times g sine theta 1, but I have to bring it to either side, so it's minus m1 g sine theta 1. That's where that comes from. Then you divide by the parenthesis, and that gives you what mass 3 is. Plug in the numbers, and it's 151.11 kilograms. So the question was, if this one slides up the incline by 5 meters, how long does it take to slide up the incline? So the acceleration is constant, and it started at rest. And you know the acceleration, it's g over 2. But if it's going up the incline, the delta x is negative. And also the acceleration is negative if it's going up the incline, because anything up the incline is negative. So it's just this equation here, this constant acceleration equation, v0, 0, because it starts from rest, and you solve for t, and that gives you 1.01 seconds. So it takes 1.01 seconds. So we got 5 meters. And then the next part was, what is the tension in rope 1? Well, you can use equation 2. The only thing you don't know in it is T1. So you just solve for T1. That gives you the tension in rope 1. And then if you want to find the tension in rope 2, you can use, well, there's more than one equation here. Once you know T1, you can use this equation to find T2. Pretty easy. You just solve for T2. You add T1 to both sides. Subtract m1g sine theta 1 to both sides. And you get T2. Oh, sorry. I did it with M3 and A. Either way, you could have found T1. And then if you know T1, you can plug it in this equation here and solve for T2. Either way, you get the same answer. I chose to do it this way. But anyhow, so, you need to know how to use Newton's second law for inclines on horizontal surfaces, how you can use it to find accelerations or forces or tensions, cases of static equilibrium where the acceleration is 0 in both directions, projectile motion, all the stuff that we did with projectile motion, you have to know for the quiz and the test. So that's the solution for homework